All right, now in 2.5, I believe they go over everything that we just talked about again, which is great because you can never see this stuff too much. All right, and it's these blocks. Remember I talked about the S block, the P block, and the D block, and that this is how that the periodic table is arranged. All right, and it's based off of the ground state electron configurations. So here is basically the diagram that I was trying to draw above. Hopefully this is a little clearer. All right, notice you have the S block, these two rows of the left. So everything here are S1s, just like what I said. Everything here are S2s. Everything here are P1s, P2s, P3, P4, P5, P6. All right, notice 3. You see how the 3 Ds is one less number than the S and the Ps? Okay, this is 4, but we're in period 5. This is 5 Ds, period 6. 6 Ds, period 7. And remember, the Fs fit in right here. They're not showing you the Fs, but the Fs fit in right here. So you have the 4F and then the 5F. Okay, just to kind of remind you. So this is kind of a great chart. I will give you a handout in class that kind of has all this. I think it's this exact chart. Okay, this is kind of a great chart. You will not have this chart for you on the exam. You kind of have to know this. But this is how the periodic table is arranged. It's based on electron configurations, and they're all in these specific energy levels. Okay, so write the ground state electron configuration, use the noble gas core abbreviation. Let's just do one of them. Let's do TE. Let's just do TE, just for practice, just to make sure. Put this on pause. I would suggest put it on pause and go through all of them. I'm just going to go over one of them. I'm going to go over TE. Okay, so put it on pause, and we'll come back and I'll do it. All right, hopefully you put it on pause. If you didn't, do it now. I'm going over it right now. All right, so noble gas configuration. The noble gas before technetium is krypton. Okay, then after krypton, you start at 5s2. All right, and then you go into the Ds. Remember, the Ds are one less, so 4D, and they're all filled. So there's 10 rows. And then you go to the 5Ps. 5Ps, and technetium is the fourth one, so 5P4. So that would be the abbreviated noble gas configuration. You might be asking, can we do the abbreviated on the exam? It just depends on what I ask. If I say to you, write the full electron configuration, then you got to write everything out. If I say write the abbreviated form, then you write the abbreviated form. I will clearly let you know what you need to do. Okay, so I suggest that you do these practice problems on your own so that you know how to do them. Okay. All right, this is kind of, let's see, electron configurations and the periodic table and valence electrons. All right, valence electrons. Let's talk about valence electrons. So notice these are all the main group elements right here. So here is group 1, here's group 2. Then they get rid of all the Ds, and then here's group 3, group 4, group 5, 6, 7, and 8. Okay, when we talk about valence electrons, those are the electrons in the outermost shell. Electrons in the outermost shell. The outermost electrons in an atom, those with the highest principal quantum number, or shell number. Shell number. Okay, the inner core electrons are the electrons that are not the outer core. The valence electrons is what gives them their properties. Here they call it the personality, but it's the properties. Like, why are the noble gases, why do they not react with anything? Well, it's because of the electron configurations, because of the valence electrons. Okay, so how do you tell valence electrons? It is very simple. All of the 1As have 1 valence electron. All of the 2As have 2 valence electrons. All of the 3As, I think you can guess it, have 3 valence electrons. What do you think all of the 7As have? How many valence electrons do you think the 7As have? That's right, 7. Okay. The Bs don't work as nicely. I'm sorry, yeah, so, or like the D block, all right, or the F block. It's not as straightforward. We're not going to talk about their valence electrons. When you take Chem 111 or the higher ones, you will talk about them. Okay, and all the inner core ones, or the core electrons, are the ones other than the ones in the outermost shell. Okay, so for example, fluorine. Fluorine is a 1s2, 2s2, 2p5. All right, the outermost shell for chlorine are the 2s. Okay, the 2s and the 2p. So there are a total of 7 valence electrons. The inner core electrons is everything left over. There are 2 core electrons, or inner core electrons. Let's call them core electrons, CE. Okay, so that's kind of how you look at it. Now, a lot of people think, well, doesn't chlorine have 5 valence electrons? No. I understand what you're doing. You're doing the outer, but what you're doing is the outermost subshell electrons, not the outermost shell. Remember, the 2 is our shell. The S and the P are a subshell. It's the outermost shell. It's all the electrons in the number 2. It doesn't matter that it's split into S and P. The total are in the 2, and there's a total of 7 of them. That's why it's just easier just to look at the group number, and you'll always know how many valence electrons there are. Okay, so here's another problem. Identify valence electrons. You can kind of do this on your own. Okay. Okay, electron configurations and the periodic table. So Lewis dot structures. So Lewis was a scientist that was getting tired of doing electron configurations and wanted to come up with a way to just quickly donate these electrons in form of dots. And it also told you a lot about the reactivity of these atoms, and it kind of hinted as to how they bond. Okay. So a Lewis dot structure basically is you start with one, so like lithium, for example, all right, has 1 valence electron. So you can start it at 9 o'clock or you can put it at 12 o'clock. It doesn't matter what spot you put it in, okay? And then beryllium, all right, there is 2 valence electrons, so 1, 2. All right, boron, you're going to have 3 electrons. And you keep going around until all 4 spots are filled up, until you're 9 o'clock, 12 o'clock, 3 o'clock, and 6 o'clock. And it doesn't matter what order. You see how they put it like opposite? It doesn't matter if you do that. If you want to do that, that's fine, but it doesn't really matter. Once you get to row 5, that's when you start pairing up your electrons. So once you get to here, you start pairing up. So nitrogen has 1, 2, 3, 4, 5. Then oxygen, 6. 1, 2, 3, 4, 5, 6. And then fluorine has 2 paired, and neon is all paired up. These are what's called lone pairs. Lone pair of electrons. Okay? So oxygen has 2 lone pair of electrons. 2 LPs. We'll call them LPs. Okay? And this tells you something about reactivity. The goal for every single atom is to have the maximum number of electrons in its outermost shell. I'm going to repeat that again. The goal of every atom is to have the maximum number of electrons in an outermost shell. That means everything wants to be filled up and paired. Notice there are 2, 4, 6, 8. It's 8 electrons with the exception of helium. All these are 8. And we're going to learn next chapter there's something called the octet rule. I'm kind of giving you a hint as to why we're even learning this. Everything wants to have 8 valence electrons with the exception of helium. So it's going to do whatever it can to get 8 electrons. So fluorine only has 7. So fluorine in nature wants to gain 1 electron, so it has a total of 8 valence electrons. Okay, so if fluorine were to gain an electron, fluorine would have a -1 charge. And we're going to start talking about this when we start talking about ions. Oxygen wants to fill up both of these spots, so oxygen wants 2 electrons. Nitrogen wants 3 electrons. Carbon wants 4 electrons. Okay, boron and beryllium and lithium, notice they also want 8, but do you think it's lone energy for boron to lose these 3 or to gain 5? It's going to be lower energy to lose 3, so it looks like helium. So in that case, it's not an octet. The rule is better to actually be called the filled valence shell. So, but you know, if we look at like sodium, for example, sodium wants to be like neon. It wants to have the same, wants to be full electron count. So it's going to lose that 1 electron. So pretty much everything in the 1As want to lose electrons. All right. Everything in the 2As want to lose 2 electrons. These all want to lose 3 electrons. The 4As you kind of talk about when you get to organic chemistry because they can do both, lose or gain. Everything in the 5 want to gain electrons. 6 want to gain 2 electrons. 7 want to gain an electron. All right, but this kind of shows you, instead of writing out, like for example, fluorine, instead of writing out the orbital diagram that looks like this, okay, with all of its electrons. Oh, I did one too many shells here. So here's the 1s2, here's the 2s2. I don't know what I'm doing here, going too fast. Okay, so instead of doing this, so showing you see how fluorine has 3 paired, 1, 2, 3, 1, 2, 3 paired, and 1 unpaired. So rather than just doing this, which looks confusing, do this, and you can just easily look at the valence electrons without worrying about anything else. Okay. Okay, so these are some trends that you kind of have to memorize. All right, size of atoms. This is very interesting. As you go across the periodic table, so I'm going across lithium, beryllium, boron, carbon. So I'm going across the periodic table. Notice it gets smaller. You would think it would get bigger because you're getting more electrons and more protons. You get bigger, but we're not going to talk about in this class why this happens. You just have to memorize it. If you are curious, you can come to office hours. I'm more than happy to explain it. Or if you want to talk about it in class, I'm fine with that. Okay, but as you go down, it makes sense because I'm increasing my shell number. So you increase as you go down, which makes sense, but then you decrease as you go across. Notice it's increasing as I'm going that way, but it decreases as I go that way. Okay. So this is kind of a classic problem. Indicate which is larger. Is aluminum larger or phosphorus? All right, well, I can look on this chart and tell, but if you look on the periodic table, aluminum is further to the left of the periodic table, so aluminum should be larger than phosphorus. I won't have this chart for you on the periodic table. I will have the periodic table for you, I'm sorry, on the exam or quiz. I'll have the periodic table for you. You just have to know that it's larger on the left and it gets smaller as you go across. Okay, metallic character. Okay, we talked about this line in chapter 1, right? Things to the left are more metallic, things to the right are less metallic. So you don't really even need this. You kind of know as you go to the left, it becomes more metallic. I think these arrows are confusing. It's saying as you go to the right, you get less metallic, which is true. These are the nonmetals. These are the metals. Okay, and as you go down, you increase. Okay, so that should be so. Basically, francium is the most metallic atom. All right. Next one is ionization energy. There's a lot of information. I am not going to read this, but basically ionization energy is the energy required to remove an electron. All right, for an electron to come out. Metals, the more metallic, okay, the easier it is to remove an electron. So francium is the easiest to remove because it's the most metallic. The reason is because imagine I have a nucleus, all right? I've got lithium that has its 2 shells, all right? And then I have sodium, which is shell 3, and then I have potassium, which is bigger. So francium is a huge atom and lithium is a small atom. These electrons in lithium are held together much tighter than the outer electrons in francium. So because these electrons are not held as tightly because of the nucleus, it can easily pop off. Where these electrons have a harder time popping off, but it does want to pop off. Okay, so that's why francium is easier, or has a an ionization energy that favors the removal of an electron. And then the least most obviously would be helium or fluorine. Right, around here is the least because those don't want to lose electrons. Those don't want to ionize. Okay, they actually want an electron. They have a high electron affinity. This is the opposite. This is where it wants to gain an electron, the ability of an atom to gain. Okay, so in general, an atom that loses an electron easily will not gain an electron easily. Okay, which makes sense. If it wants to lose it, it doesn't want to gain it. Okay, so this leads to the essentially the opposite trends for the two processes from left to right within the atoms. Okay, so fluorine, all right, easiest, cesium hardest. Okay, so higher electron affinity as you go from left to right, and as you go from top to bottom, higher electron affinity. Okay, it makes sense. All right, last, let's talk about ions. Ions are atoms that have lost or gained electrons. All right, an ion is something that has lost or gained an electron. Okay, and there's 2 types. There's cation. This is pronounced cation, not cation. Do not pronounce it cation. I am pronouncing it correctly when I say cation. All right, and this is an anion. Cations have positive charges. They lose electrons. Anions gain. They have negative charges. They gain. Pretty simple. Cation has a T on it, which looks like a positive symbol. Anion has another N for negative. Easiest way to remember it. Okay, so like sodium has a plus charge, so sodium is a cation. This is a sodium cation. Cl minus usually has a negative 1 charge. This is called a chlorine anion. Okay, and they're going to gain and lose electrons depending on how many it does, so that it has the same electron configuration as its closest noble gas. Like I said, we'll learn about that in another chapter. So let's talk about this term isoelectronic and how it affects the electron configurations. Okay, so if you look at the periodic table, if you look at calcium, so let's look at the periodic table. I kind of wish they put one here because these drawings are not that great with this. With this. Well, if you look at the periodic table, do they have one here? Perfect. Yeah, okay. Here is calcium on the periodic table, all right? And if you look, argon is right here, okay? And then krypton is right here. So notice that our D block is gone. So calcium is right here. Calcium is going to lose 2 electrons so that it has the same electron configuration argon. It's closer. Argon is closer to sodium than krypton is. Calcium is 2 atoms away from calcium. Krypton is, these 5 plus all the D's, so it's pretty far away. So it wants to have the same electron configuration as argon. So it's going to lose 2 electrons so that it looks like argon, has the same electron configuration as argon. Okay, so that's what they're showing you here. Calcium itself has the electron configuration as argon, as a noble gas configuration of argon, plus 4s2. Okay, however, it wants to lose these 2 electrons so that it has the same electron configuration as argon. Okay, now, I don't like this slide. You never write an electron configuration as a noble gas. So technically, the way that you would write this would be neon 3s2 3p6. This is the right answer. They're just kind of showing you how it now became like argon, but never do this. I want you to actually draw out the previous noble gas plus whatever's left over. Even if it is a noble gas, you still have to do this. Okay, and this is what's called isoelectronic. It means the same electron configuration, but a different atom. So calcium 2+ is isoelectronic with argon. Okay, calcium 2+ is isoelectronic with argon because they different atom but same electron configuration. So phosphorus, sulfur, chlorine, potassium, these are all isoelectronic with argon, meaning they have the same electron configuration as argon. Because phosphorus gained 3 electrons. You have to remember negative in chemistry means gaining electrons. So phosphorus 3- has the same electron configuration as argon. All right, all their electron configurations are 1s2, 2s2, 3s2, 3p6. That's the electron configuration for argon. That's also the electron configuration from Cl-, for Se2-, for P3-. Okay, like if we were to take sulfur, I'm going to show you this by looking at an orbital diagram. Sulfur is 1s2, 2s2, 2p6, 3s2, 3p4. Okay, let's look at the orbital diagram, just so we can get practice at orbital diagrams. So remember, this is 3. And all we care about are the valence electrons, but I'll just draw them all out just so it understands. So we have paired here, everything here is paired, everything here is paired, and this is 4. 1, 2, 3, 4. Notice I've got 2 empty spots. This needs an electron and that needs an electron to have this completely filled. All right, or move over 2 spots. 1, 2. Okay, so if I were to put 2 more electrons in here, it now is an electron configuration of 3p6, which is the same as this. And notice it gained 2 electrons to get there. So that's why sulfur has a 2- charge, because I added more negative to the atom. I'm adding more negative. Think about it. I'm adding something that are negatively charged, so it becomes a 2 negative. Okay. Negative in this case means I'm adding electrons. Okay, so here are some more problems. I suggest you work on these and make sure that you get through them and that you understand them. Okay, Lewis dot symbols, pretty straightforward. If it's a plus charge, you don't put electrons around it. You just put a plus. For ones that become negative, you put all 8 electrons around it. So like Br minus would look like that. Okay, calcium 2 plus would look like that. That's the Lewis structure. That's all that is saying. So again, here's some problems. Do the Lewis structure of the cations and the anions. Okay, they kind of show you if it's plus, you don't write anything. If it's negative, you put the electrons. Okay, so that is the end of chapter 2. There was a lot of information here. Please, please, please write questions. If I've said anything in the video that doesn't make sense, if I've said the wrong thing, sometimes I'm notorious for saying that. I probably said like a 3P and I meant to say 3D. Please make me aware of it in class so that people aren't confused. All right, but hopefully after this, and then after we talk about it again in class and do problems, things will make more sense.